Hello and welcome to another PlayBASIC live video. Today I wanted to talk about number systems, but rather than sort of go through decimal and binary and hexadecimal, I thought I'd actually take you back on a bit of a history lesson and use one of the examples that's found in the forums. I've already sort of been across there and had a look, but if you have a look at the forum, there's the section called competitions. And there's a section here called Clever Coders. And these are kind of just challenges we throw out to people. One of the challenges was inspired purely by this problem. And how do you teach people? It's one thing to show people a binary number and how to convert those things across, and then sort of users go, well, okay, well, what does that really mean? In this example, we actually do something that old retro programmers had to do. They had to know this stuff before you could do anything, and that's actually using binary operations and dealing with pixels in general in a kind of an emulated sort of retro display. So, written a bit of code here to show some of the stuff. So the example is in this part of the forums, and it's attached down the bottom. You do have to be logged in to download attachments, but anyway. So I've already downloaded it for us. Head across to PlayBASIC, and I've loaded it already. Hit reopen. I like this idea of how to teach people this stuff, is because you have to jump in and sort of understand what's going on. Now the example kind of looks like a kind of normal PlayBASIC program until we've got this rendering code down the bottom here. It's drawing, well, let you sort of work it out yourself, really. We're doing a bunch of pokes into our screen memory of this binary numbers here, which is, if you look carefully, you'll see the letter A coming up in there. If we just run the example quickly, hopefully we don't lose audio sync with this one. Right, so we're drawing the character A to our simulated. Got a few other functions in there as well, like dots and boxes by the looks of things. Let's go back. The reason I think this is a good way to get stuck into learning binary in particular goes back to when I was a kid, and we sat down in front of the good old Commodore 64, at which you have very limited memory, and to do anything graphical requires that you know binary operations. You have to be able to make a sprite. You've got to poke this thing into memory. And it's one of the best ways to teach this stuff is by doing it. So there's a whole bunch of information here on the 64 if you really want to have a look at it. I would actually recommend going back, downloading an emulator, and trying some peeks and pokes and trying to understand how the 64 works. For many people, it will be a culture shock that you'll just never be able to understand. These systems don't have, all of the lovely stuff we have now. In BASIC on the 64, you pretty much had a very limited instruction set, probably less than 100 commands. I can't remember now, possibly less than 50. And the two commands you used the most were peek and poke, and these are a poke lets you write a byte to memory, and a peek was for reading a byte from memory. So all of the video hardware you had to set up manually. You read the hardware manuals, and you had to set the correct bits to have the right sprites appearing. Classic things on a 64 were like the sprite positions were 8-bit, but the screen was 320 pixels wide. So an 8-bit value can range from 0 to 255. So how do you get it to move that extra part of the screen? There's a whole other conversation there completely. Anyway, so this is where I'm coming from. People who grew up in this era have really hands-on, tactile knowledge of accessing memory, and over the years, that's just not the case anymore. So I come up with this example which creates kind of an emulated 2-bit display. What's it called? Retro computer environment, and it has an include, which is all the functions over here that make up this little retro computer. So video memory is 80 bytes wide, not pixels, bytes. It's 400 lines high. We're computing actually allocating some memory in a bank and getting a pointer to it, and that's our video memory location. We've got 2 colors. Each pixel can either be on or off in each byte. So we've either got kind of a darker blue color or a sort of darker, a brighter, almost kind of white color. Functions for doing things like getting the screen width, screen height, screen modulo, which is the number of bytes on a row of memory, getting a pointer to the screen memory itself, getting the mouse position relative to our screen. We get down to here and we start to see we're using fill memory to do a clear screen. So we're filling this chunk of memory wherever this pointer points to, and it's the number of bytes times for one row times the number of rows. That's the number of bytes to fill. Come down here and look at the RCE dot command. Because our pixels in our retro computer example here are in a format called planar. Modern computers use byte per pixel or long words or integers for each pixel in memory. Very simple way of storing pixel data. But old computers didn't. In fact, they used a whole bunch of different methods, in fact, to do this stuff. And one that's used on systems like the Commodore Amiga and variation of it is on the Atari ST, is planar. And if I just sort of draw a bit of an example there here in just bits. Let's say I've got a character that's 32 by 32. I'll make a template first. So each byte is 8 bits, so I need 8 bits. Okay, I've got 8 bits there. That's 16, 24, 32. So that's a row of 32 pixels. Each pixel can either be 0 or 1. And every 8 bits is a different byte. So that's the first byte, second byte, and sorry, I've missed a character there. I think I just deleted one. Alright, so we've got 4 bytes in that. We have rows. We could have rows of this stuff here. So I could have all these bits here are set. Yeah, just making a bit of a mess there, aren't we? Just thing. I've got a few extra bits there. So each binary number here, which we wouldn't have the spaces in them, these are 32-bit binary numbers. In old computers, we'd only have dealing with 8 bits at a time, so a byte at a time. This is how graphics memory is actually stored. So our graphics memory in this example is at this video memory pointer thing. There's so many bytes across. So and each byte has 8 bits in it. So you can have to work out when you draw a pixel, you've got to work out what byte on the row it is, and then what bit within that byte you need to set or clear. So this is why this dot routine down here is quite confusing to look at. So we've got a dot, which is we can have it's either color 0 or color 1. It can only be one of two things, either on or off. So we're masking the color to make sure it's no other weird value. We're getting the address of our RCE frame buffer. Then we're computing. We're taking the x coordinate, which is in pixels, dividing it by 8 to convert that from its pixel value into the bytes. How many bytes from this left hand, from this side of our image across are we? So if the x coordinate was 0, we're going to end up with 0. If it's like x coordinate's like 4, it's going to be 4. But when it's say 8, we're 1 byte across in this row, but we're still actually in this bit. Then we have to work out which bit of that byte to set. I know that's pretty confusing. I realize I'm not making a lot of sense. Okay, so we're computing the offset along the row, along the x-axis, and then we're doing a bit of what looks like crazy binary weird stuff here to set the pixel. But I could rewrite this as using a hex value there. We could just write this as binary. So this 8 zeros, that's setting the high bit within the byte. In binary, it would look like this. So this bit here, what did I set then? That's the equivalent. So what we're doing is we're working out, we're asking the x value, masking off the, we're keeping the bottom 3 bits of it, which is, since the row is divided by 8, we need to know the remainder. Now to set the pixel, right, so if x was 8, for example, which would be this bit here, across any one of these rows, doesn't matter. This expression would be 0. All we're doing here is we're shifting this result, this number of bits. So in this case, we'd be shifting this no bits at all, so bit would end up being this. If x position was 9, though, we went through this same expression. If x was 9 and we mask this by 1, we actually get 1. And then we're shifting this value here across 1 bit. So we're shifting it across like that. See how it's in this part of the byte now. If x was 10, this would be a shift of 2 and 2 bits. Okay. Now we're doing a bit of a, oh, what have I done there? Sorry. Not used to this keyboard still. Here we're actually doing a subtraction, and what we want to do is we want to get the inversion of it. So in bit terms, we're doing this. I've used hex there. If we use, so this 55, so FF value is this in binary, 1, 2, 3, 4, 2, 3, 4. Right. Let's make an example. So let's say if X position was 10 again, we would compute bit. We'll do it down here. Sorry, this is terrible, I know. It's 10. We're doing a shift of 2. Bit is this value here. Oh, sorry, I've got a few extra zeros in there. When we do this, when we subtract this from that, we get this. That becomes the mask. The mask is important when we want to clear a pixel. If we have multiple planes, so we would need to mask it as well. Anyway, so this part here is dealing with computing the x-axis stuff, working out what bit and computing the mask, what byte within the row, and then moving the mask so it's within the right position. Now we're computing the y coordinate inside the video memory, adding it on to our video memory pointer. We've already added on the x-axis up here, so this is actually the byte we're going to access, which we're doing here. Reading that byte from our video memory, and we're ending on the mask to clear the bit we're about to write to. And then we check which color we want to write. If we want to write color 0, then this is going to be skipped over. If we're writing color 1, this will be executed, so we're masking on this bit value back onto it, and then poking this new byte back into memory. That's how cumbersome dealing with planar graphics are. And it's one of the reasons why it's a great way of learning this stuff. There's an alternative demo here. I haven't actually grabbed that one. I'll just grab this bit of code. It's on the forum as well. I don't know what it produces, so we'll soon find out. Go back here to our demo. I just paste that at the top and just delete whatever's below it. Hopefully that's going to work. Okay, so we're doing. Oh, okay, we've got a much more advanced version of our character writing. The previous demo would only draw characters. Could only draw a character when it was perfectly aligned to every 8th character, and that's how memory is laid out. Okay, so we're doing a quick look at the inner loop here. We're clearing the back buffer of our pretend retro computer screen, getting our mouse position on our retro screen, asking the state, just in case we want to draw a dot or something like that. We're pulling this out of data, which is a bit silly, but we are. Render sprite bits to frame buffer. So let's have a look at that function. And this is rendering this row of bits. This is what drawing sprites was like manually on these old computers, and why you notice a lot of old games, the characters jump 8 pixels at a time, particularly on the VIC-20. Check them out sometime. You know, when you see games that actually have true sprites on those systems, it's a bit of a miracle, really. So this thing here we've got a byte worth of bits for our sprite. We're doing some clipping to see are we inside the screen or not. We're working out where we are down from the top of the image, top of the screen image down to the row we want to draw to. We're computing our offset along the x-axis. We're rounding it to what byte we need to be on along that row. We're working out how many bits of shift we need to move our set of pixels. We're adding our pointers together to get the actual location of this thing in memory. And now, because it's a sprite, we actually need to read the target memory where we're going to write to, because we need to preserve some of that and modify some of it. So reading from the screen memory, we're getting our sprite bits, shifting them to the right, and then ORing it to this byte, then placing this back in screen memory. Now, when we do a shift like this, just doing a quick example here. Let's say we had a binary number, or these. This is the bottom there. Let's use that one there. So these bits here. If we were drawing these bits here, and if I shift this value, let's say 4 bits to the right, we would end up with these bottom 4 bits get lost, and you end up with that. So the bits that are lost, we need to preserve those and then write them to the byte beside where we were drawing before. So what it's doing here is a bit of a workaround for that, really. It's going, is the shift value anything, is it bigger than actually 0? If it is, okay, we move to the byte next to the one we just wrote to. Check that it's inside the screen, the right hand screen boundary. Compute the address, and then we read this byte, do it. And we write the bottom bits by shifting it the opposite direction into the byte next to it. And that lets us do a real 8-bit sprite. That's how you would do sprites in old systems. I know this is not a very appealing sort of thing to do, but if you really want to get into raw memory access, learning a binary, learning shifting and masking, things like AND and OR, XOR, this is the way to do it. Jump in, have a crack at it, and because you can't really fail. The program probably will crash if you do some weird stuff with it, but that's the beauty of this. Just like going back to those old 64 days, those systems were, you either got it right or you didn't. When you didn't, it broke and crashed, and that was actually a good thing. I think today what's taught with the sort of information technology in general is very high and abstracted from how a computer actually works. And when we're making games, we tend to need to actually know this stuff, get down to the nitty gritty and know how our bytes are stored in memory, and how it's invaluable for dealing with file formats, for example, or storing more information or packing information together. Okay, I think I've talked a lot about that. So if you want to grab this example, head across to the forums. It's in the competition section over here under Clever Coders, and I've forgotten what it's called already. It's called Learn Binary Operations Through Retro Computer Graphics. And these are kind of challenges we throw out to people. Obviously, no one's really had a crack at doing this one here. I've posted a link to a version of Elite. Elite was written in I thought it was 83, but it's probably is 84. It's got wireframe graphics, the works. It's doing things that people just didn't really thought were sort of not really plausible on these old computers. Drawing a line on a planar-based display is very challenging. And if you don't believe me, download a little retro computer environment and give it a go, and you'll soon see why it's so challenging. It's easy if you make a dot command and just call the dot command over and over. That's easy, but it's incredibly slow. The box command here, for example, I think I've wrapped the dot command. Like, this is terrible. If you try doing this stuff on retro computers, it would just absolutely choke. Anyway, that's enough for that chit chat today. So if you want to learn some binary, get into some hex, have a crack at this. Thanks for watching, and we'll catch you some other time. Bye.